Welcome, YouTube. For those of you that follow this channel, you'll know that we make documentaries with leading cosmologists about competing models for the very early universe. And one theme that continually arises is if we're going to understand nature at the extreme conditions of the Big Bang, we're going to need to combine our theory of the larger scale structures in the universe, Einstein's theory of general relativity, and it's a theory of gravitation, with our theory of the smaller scale in the universe and the other forces of nature, quantum mechanics. In short, we're going to need a quantum theory of gravity. And this has proven to be a very difficult task, but one idea has dominated the frontiers of theoretical physics, shall we say, and that is string theory. And while string theory has been very, very prominent and impressed many, many physicists, it's probably fair to say that not everyone is happy with its prominent position. And some physicists have developed alternative approaches, most notably perhaps loop quantum gravity. But string theorists have replied that these alternatives are either going to be incorporated into string theory or prove to be dead ends. But one thing I think has been missing from this conversation is an actual conversation, and one that perhaps a layperson might be able to follow. And so I'm really, really excited today. We're going to try that. And I'm we're so fortunate and lucky, and I'm so thankful that we've got two of the biggest names in physics joining us for this. Firstly, we have David Gross. David won the Nobel Prize in Physics for his work on the strong nuclear force. And it's been said that the papers that led to that were the last ever theoretical physics papers written in the early 1970s to be awarded a Nobel Prize. David has also been a pioneer of string theory. He's associated with what's known as the Princeton String Quartet and working on what's called heterotic string theory. And Sylvester Jim Gates, the current president of the American Physical Society, has described David as an Olympian of string theory. So welcome, David. And we also have Carlo Rovelli. Carlo, along with the by Ashtekar and Lee Smolin, is known as one of the three founding fathers of loop quantum gravity. And he'll be well known to many people through his popular books, particularly 7 Brief Lessons in Physics, which has sold an uncountable number, I imagine. And his new book is Helgoland. Although I do recommend his very first book, I think it's overlooked, Anaximander, the First Scientist. These are beautifully written books, and I think deservedly, Carlo has been called a poet of physics. He's also been labeled as one of the 100 most influential thinkers of our time. So welcome, Carlo.
Thank you, Phil. Thank you very much.
So David, why don't we start with you before we get into our heavy conversation? Perhaps you can just let us know a little bit about yourself. How did you get interested in science and in physics in particular?
Well, as a teenager, I started reading popular science books, and I just wanted to congratulate Carlo on writing very nice such books, which are really often a way where young people get attracted to science, especially theorists. You know, it's easy to play around in the laboratory, but I was attracted to, theoretical physics. So the first reading a book I was given on by bar mitzvah by a cousin of Leopold Infeld, who wrote with Einstein a wonderful book on the theoretical physics, which I still have. So, rather early on, I really wanted to do theoretical physics.
Right. And Carlo, so David was early to physics. I believe you were quite late to physics. Is that right?
Yes, my path into physics is it's a different one. I got late into it. I was as a young man, I was very curious. I read all sorts of things. I was passionate about learning, but I was going all over. And I did not have a specific, in fact, I started studying physics a little bit by chance. It sounded interesting. It sounded central. It sounded that somehow if I wanted to know what science tell us about the world, I had to know about physics. But I didn't think about going into that. It's only while studying physics, and in fact, it's only when I got to modern physics that it was like a flash for me. Oh my God, how beautiful is this? I mean, how beautiful is relativity? How beautiful is quantum mechanics? And how deeply affects our view of the world. And then I got trapped by this.
David, why don't we sort of get into the meat of string theory? There's a simple question, but maybe it's not so simple, which is, what is string theory? And in particular, I'd like to know, how is it seen back, let's say, in the first string theory revolution? And then how is it understood today?
Well, string theory is a story in evolution. It's like science often is. String theory is actually 53 years old, which is quite remarkable. And it started out in 1968 in a very phenomenological way, trying to understand features of the strong nuclear force and guessing an expression for the what are called the cross sections, the probability amplitudes, that when you throw two protons together, what comes in, lots of particles come out, different probabilities for different outcomes. What are the rules? A lot was known experimentally about the strong nuclear force, but there was absolutely no theory to guide one. But there were rather strange features, and in particular, ones that indicated, in today's language, that there's a way of thinking about strongly interacting particles, which we now know in QCD are composites or bound states of quarks, which are held together by a field, much like the field of electricity and magnetism, but it acts on the colors, the three colors that label quarks. And we now know that, that field creates a force between the quarks and holds them together. But just from the data, people were discovering properties of these bound states of quarks that we would say today would indicate that there's a way of describing these states, quark, anti-quark, as strings. We now understand that as due to the properties of QCD that squeeze the flux of the electric and the chromodynamic fields that give rise to the forces into narrow flux tubes that connect the quarks instead of expanding out over all space. And that gives rise to a constant force as you try to pull the quarks apart, and we now understand is the reason quarks are forever confined in the nucleon and why no one has ever produced a quark, a free quark in the laboratory. But building on these phenomenological ideas, trying to incorporate them in mathematical formulas describing the amplitudes that experimentalists measure, people hit upon some remarkably simple formulas that that seem to offer the possibility of constructing a theory of the strong nuclear force. Now, that didn't turn out to be successful, but that was the beginning of string theory. And it's very interesting because it really started from the bottom up, from experimental data and experimental facts, the existence of these flux tubes, in effect, and then led off into mathematical formalism that acquired a life of its own. And so this started in the late 60s, 1968. I got very interested in this since I was focused strongly on the strong force, and spent some years trying to understand this stringy. Originally, it wasn't even called string theory, and people had no idea that there were strings involved. It was just a mathematical formula, but it had a life of its own. and it was simple and extendable and could be developed into a theory, a quantum mechanical, relativistic quantum mechanical theory of something that made complete sense. And but remarkably, so it's quite a remarkable story, because starting from data, one hit upon a mathematical model which had a life of its own and has been evolving now for over 50 years. But that evolution, that development of what string theory is maybe in its teenage. It's certainly not mature and adult and completed. So it's an evolution. The evolution has been remarkable in the amount of content and development that has taken place. One of the earliest things was, in effect, the discovery of gravity. So within this formalism, which was not, gravity is quite irrelevant at the LHC. It's a very weak force at low energies, unless you get big planets, so black holes together. But the formalism, the mathematical consistency with quantum mechanics and relativity, special relativity, led to certain outcomes that could not be avoided, such as the fact that this theory contained gravity. The theory contained gauge forces, the kinds of forces that give rise to electromagnetism, to the strong and weak nuclear forces, the elements of our standard model of particle physics. All of that was forced on one following this direction. And as the strong nuclear force was solved by QCD, attention then turned to say, well, let's try to use this formalism to describe all these other forces that are forced on one. A lot of discoveries, theoretical discoveries, were made in this framework. In fact, the realization of supersymmetry, of symmetries that involve anti-commuting variables, fermions, again was forced on one, or one was led to, by this mathematical journey of exploration. The possibility of extra dimensions of space-time, an idea that goes back over 100 years to Kaluza, shortly after Einstein's theory of relativity, was forced on one. And you referred to the string revolution. That was an explosion of activity, 1984, 5, where realistic models that were consistent in a perturbative expansion, which contained all the ingredients of what we know about physics, and we know a hell of a lot with the standard model, appeared naturally. So one was, had the exciting possibility of trying to use this formalism to construct unified models of gravity, which had to be included, and the other forces of nature, of which we know an enormous amount. Literally tens of thousands of experiments have been performed. Standard model works beautifully. We have a very good constraint on trying to construct more elaborate theories. That effort developed, created an enormous amount of activity and excitement, because there's nothing, believe me, as a theoretical physicist, more exciting than believing that one is in the situation where one can, one, make predictions that can be tested, or two, explain various things that have been measured for which there is no explanation. As it turned out, life and physics is much more complicated, and our understanding of string theory, or whatever it is very young and undeveloped. Uh, the problem turned out to be that there wasn't just one consistent theory, unified theory, but lots of unified so-called theories or different possibilities for what the world would look like. And faced with the problem, the experimental problem that experimenters so far haven't found almost any deviations from the standard model, there are very few clues as to which of these many possibilities one should pick out. But even more troubling from a theoretical point of view, no deep understanding of what principle could pick out a consistent theory from the vast framework of possible theories that string theory provides.
Right.
Finally, there was a third revolution that occurred in the 90s and still is with us, its implications, and its which is the so-called duality or holography revolution, where it was realized that string theory can provide a dual description of what can otherwise be described by what we would call ordinary quantum field theory that we use for the standard model. This goes way back, this goes back 50 years to the origins of string theory, which we now understand as a dual representation of the flux tubes of QCD. QCD is a field theory, no gravity, but can be thought of, and in certain cases, that correspondence is quite explicit and well understood. Not for QCD yet. That's a problem for this century. But that duality between ordinary quantum field theory, which we understand very well and can solve and can test with experiment, and string theory has proved to be extraordinarily fruitful with many, many applications to QCD, to standard model, to condensed matter physics, to many areas of ordinary physics. And on the other hand, the duality of what we know about ordinary quantum mechanical systems can then be applied to quantum gravity, where we know very little. And that has been, again, extraordinarily successful in furthering our understanding of black hole physics, especially. And hopefully someday, although I think it's quite distant, quantum cosmology. But the journey is still going on, and it is unclear how many of these revolutions or big insights will be required. It's not finished. What has changed is, for sure, the realization, see, in the beginning it was thought, and what attracted me originally, I must say, in '68, was the idea that this was a totally different, separate approach to relativistic quantum mechanics. And different, fundamentally different than quantum field theory, in the same way that quantum mechanics is different than classical physics. I think this is sort of what motivates some of the loopy guys. They think that their approach is a totally different way of starting and looking at things. What we realized in the 90s was that it isn't different. It's just a different way of looking at exactly the same thing. That there is no distinction really between quantum field theory and string theory. Quantum field theory, which is our most successful theoretical framework in physics ever, and has been, tested and over and over again in the standard model, is still much ill understood. And string theory, or the theory which involves extended objects and is a dynamical theory of space and time, is, we now understand, a different way of looking at processes in physics, which can alternately be described by relativistic quantum field theory. So I don't regard string theory and field theory now as different subjects. They're just different parts of a very broad framework, which is extremely powerful. And where it ends up, what the total landscape of and the deep answer to the question, what is string theory, that remains for the future.
Okay, thank you. Thank you for that, David. So Carlo, one of the reasons I particularly wanted to have you on is that you were invited to write a review of string theory from an outsider's perspective by Foundations of Physics. And I was wondering if you could sort of outline, what did you say in that review? What were your main thoughts from someone that works on a different approach? How do you view string theory?
Thank you. Well, let me make let me start by thanking David first for this conversation. David and I have met a few times at conference. We have a few conversations. I don't think we never had we never sat down, talk physics extensively, sort of comparing views at all. Of course, I've done that with many other people who do string theory, but never directly. I see these conversations, whether in private or in public, very useful. Not so much because we're convincing one another, of course. I mean, we have different views, and that's fine. But because it's good to have different views laid down, which come from different communities. Science is a funny business because it's always struggles for consensus, but you build consensus through disagreement and through different communities that go in different directions. And this conversation are the moment in which you compare points of view, both for ourselves and for others. I mean, every time I have one of these conversations, something changes in my view of things. But I have to say that I'm particularly happy to have this conversation with David, rather than anybody else in string theory. By anybody else, I mean anybody else, for a very specific reason, which I want to emphasize here, because David is a great scientist, obviously, and he has got a Nobel Prize, he's recognized universally, but he hasn't got a Nobel Prize for his work on strings. He got his Nobel Prize before, because he's one of the architects of the Standard Model. I mean, if we have this, perhaps the most successful theory of physics, at least empirically, ever, the Standard Model is because of a certain number of people, small number of people, and David is one of the few. QCD, it stands together thanks to his work. Now, why this is important for me in this conversation, because I'm going to criticize string theory and to lay down what I myself and other people, in fact, large communities of people, think are the reason for not being so excited about string theory as much as some people working string theories are. And it's very hard to criticize somebody directly, at least for a personality like mine, because you're just telling to people, your life work is it's wrong, it's going nowhere. But with David, there's no risk of that, because he's great enough a scientist, is completely independent of string theory, right? He has put QCD on its right foot. So even if string theory is a total failure, which I think it is, the greatness of David Gross as David will remain in the book of physics.
Okay, Carlo, enough apologies. Just go ahead.
This is important also because I think the description you gave of string theory, I would subscribe to it. I mean, you describe well the way it developed. You describe well what it is, and also what has fascinated you and other people working in it. But exactly the same story with the same events can be described, and in fact is perceived by people outside the string world in a different manner. Namely, today you say the theory is in its early development. It's a young theory. We don't know exactly what the theory is. We know it's a different way of, we can think it's a different way of thinking of field theories, but we don't even know the sort of fundamental equations of string theory, so to say.
No, I'm sorry. In certain situations, we do, for sure. So, in fact, one of the outcomes of this duality revolution was the fact that in certain situations, one has now. So, there's a difference between, I try to make this distinction between a theory and a framework. And it's often confusing what we mean by a theory.
Would you agree with saying we don't know what is the theory?
Quantum field theory is not a theory, it's a collection of theories. It's a
maybe you talk for 15 minutes. Yeah. Maybe I continue my
I just want to make corrections along the way when you say.
No, it's better you don't.
Equations.
You don't.
Okay, let me just interrupt for a second. Carlo, if you could just come to your criticisms of string theory.
Yeah. Wait a minute. I mean, David has talked for what? 10 minutes. Now let me talk for 10 minutes.
He has. So if you come to your criticisms and then we'll let David respond. Is that okay, David?
So I stand on my point.
Yeah, go for it, Carlo.
The reason string theory could be interesting is that if it would correspond to a set of precise equations that describe the world. And I think that there is agreement among many of the string theorists I talk to that this is not known. Not only that, but when there was the big enthusiasm, the moment in which there was the maximum excitement of string theory, which as David says is the second string revolution in 84, 85, there were very precise objectives that seemed very close by. People were hopeful to have these basic equations in which there was only one or two, or a small number of fundamental constants, out of which one could compute the free parameter of the standard model. One could predict the new phenomena that could be tested. One could derive the, say, SU3 plus SU2 plus U1, the three family, and there was a lot of activity thinking that in a short time one would understand supersymmetry breaking, compactification, all the technical things that would show how to describe the world, our world, from now nothing of this has been realized. None of this problem has been solved. Now people don't talk about string theory as a theory, but a framework, which means that within a framework we should select a theory, and we don't have the theory anymore because maybe it's a boundary theory, but which boundary theory? And people say, well, there are different things that might be related to one another. And I think Polchinski summarized very well this in a conference, fortunately, a few years ago, before he left us, saying string theory is a wonderful theory based on a single principle, a single basic equation, but we don't know this principle, and we don't know the single equations. But more importantly, I think there was a strong hope in the 80s that in a short time, there would be predictions coming from string theory that would be verified. And there were predictions, not predictions, there were suggestions, empirical suggestions from string theory, which were considered extremely plausible by the entire string community. The first one was, for instance, that the cosmological constant be negative. So much so that when the astronomers started measuring a positive cosmological constant in the sky, the community, the theoretical community of strings didn't believe it very much. And then they were wrong. And the most astonishing thing that happened recently is that a huge community was convinced that supersymmetry was going to be found at CERN, at LHC. And in fact, people were almost certain on the basis of a number of arguments, dark matter, naturalness, but especially string theory and the need of supersymmetry of string theory, that low energy supersymmetry had to be there. And it was a huge disappointment. There were articles on papers saying the crisis of physics. it wasn't a crisis of physics, of course, because other people, like the community in which I am, were not expecting supersymmetry. It was only a crisis of those who expected supersymmetry. So I think that it's 50. What did you say? 40 years old, 50 years old. I don't know. The theory, it hasn't delivered what expected at all, and I think there's consensus of that. It has become, exactly as you say, I agree with that, a fascinating mathematical evolution, path of discovery in which people have turned around ideas, some of which have been applied in other fields, and that's good. So some of the success has been developing mathematical methods used for other fields, but this is very different of understanding how the world works at a fundamental level. And there is today, I would say, in the entire scientific community at large, a sense that it has been a beautiful attempt, but it has been a failure. It might still work, but the enthusiasm, the hope is not the same as 30 years ago.
All right, so David, maybe I could just summarize, let's say, 3 criticisms you addressed, perhaps. Although
I counted 4.
Oh, okay. Well, so there was no, there's no fundamental equations of string theory. There's cosmological constant was predicted incorrectly. No supersymmetry. What was the 4th one?
No basic.
The failure to come up with prediction. Okay, so again, I want to emphasize that there is no such thing as string theory. There's no particular theory, just as there's no particular quantum field theory. Now, quantum field theory is historically developed. Once one had quantum mechanics and one had Maxwell's theory of electromagnetism, not to speak of Einstein's theory of dynamical space-time, there was an imperative to quantize those theories. QED, the Standard Model, came out of that effort. But there's no question that the Standard Model, so quantum field theory after Maxwell was easy, QED was direct, in a sense, just a technical triumph of quantization of an existing successful theory of electromagnetism. But the Standard Model would never have been constructed. That's a particular quantum field theory. QCD is a very special quantum field theory. It has a whole bunch of parameters which are not calculable in the theory, and you could modify those parameters, you'd get a different theory with different predictions. There is, in my opinion, no way it would have taken centuries to find QCD without the experimental, that large, very large number of experimental facts and clues. Now, going beyond the Standard Model, we don't have any such clues at the moment. Very few, maybe dark matter. Therefore, we're really in a problem. The exciting thing about string theory, as Carlo said, the string revolution, was that framework contained all of the elements that exist in the Standard Model, which isn't easy. For example, it contains chiral fermions. So fermions like the electron, the muon, the quarks, spin 1/2 particles with a chirality, with a handedness built in to their interactions. Extremely special and often difficult and inconsistent to describe in relativistic quantum mechanics. So, and second, string theory, the string theories that one knew, the solutions along in this framework, had all of the so-called fundamental constants, parameters were dynamical. So that one had the possibility, for the first time in the history of physics, to imagine a framework in which one could have a unified theory. Now, of course, that's exciting and was hyped up, and that's the nature of physics, believe me. And it didn't work out so simply. Physics, the real world is much more complicated sometimes than we imagine with our restricted point of view. But, big deal. So what? You don't find that the issue of whether particular string theories or solutions have a well-defined set of equations now is to somewhat resolved, because for certain cases, using the holography, one can construct them even on a computer if you want, the same way we deal with relativistic quantum field theory.
Can you just briefly explain what is holography? Not everyone will be familiar with that.
Right. So holography, is a general feature, we believe, of theories of dynamical space-time, of what came out of Einstein's general relativity, where it appears that the observables and the are really exist not within the space-time, but on the boundaries or the asymptotic regions of space-time. That's where we can formulate what is actually measurable. We either have scattering experiments where we start out with well-defined states that we can describe easily, asymptotically. We throw them in and see what comes out, or other kinds of observables. And holography really is the idea that the full content, the dynamical content of the theory, can be formulated in terms of physical degrees of freedom, physical things that live on the asymptotic, the boundary in some cases, or asymptopia. But that now has a very precise formulation with so-called anti-de Sitter space, conformal field theory correspondence, ADS-CFT, or many other examples of holography, where there's a precise mathematical correspondence between a dynamical theory on the boundary, which has rigid space-time, and so is not a gravitational theory. It's much simpler, more conventional, and which we know how to put on a computer if you want. So we can solve those theories in principle. And bulk theories of space-time. And the feeling is that this is a one-to-one. You can always do this. But aside from the zillions of examples we have, it's certainly not completely explored.
So let me.
That enables us to do what was lacking before. So Carlo says there are no equations. That's true. There is no particular theory. There's a framework. There are no equations for quantum field theory either. There's QCD, and there's many examples where you just change a number of fields, parameters, et cetera, et cetera. There are many, many theories, and there are many string theories, and some of them can, we believe, an enormous amount of evidence, are exactly mathematically isomorphic to well-defined quantum field theories, which one can in principle solve, or at least numerically. And we know how to do that.
Before we move on to the other issues, cosmological constant and so on, I want to just have a little bit of conversation about this particular issue. Carlo, can you address that? The problems of no particular equation is true for a normal quantum field.
Yeah. I can easily address that. I mean, David got the Nobel Prize for QCD. For one theory. I mean, I can write the Lagrangian not because I've written it, of QCD. I mean, that describes the world. It describes a strong interaction. The open problems are things, not confinement is not proven, but we think it's right. I mean, that's a fantastic theory that describes a phenomena well with a fundamental equation. We know how to do it, not a framework. Okay, everybody can do frameworks.
No. But that's right. Quantum field theory is a framework. QCD is one point in that framework.
Yeah, but you can have a point
in this extended framework, which I can define, if you want, through holography.
All right. So all the
supersymmetric Yang-Mills theory in 4 dimensions.
So one at a time, guys. One at a time.
Defines.
David, let me illustrate Let me illustrate what many people see as the lost in mathematics, exactly by using your words. You said ADS CFT, right? Which, as you clearly described is a duality in which on the one side you have CFT, which is a quantum field theory which we control, or well, we believe we control. I mean, we know what it is.
Can we just explain? Sorry, can you explain what is ADS CFT?
I'm getting. I don't. So it's ADS CFT is this holography. It's a quintessential example of holography, and the most studied example of holography, in which it's a duality between a so-called boundary theory, which lives on the boundary of space-time, which is CFT, and ADF-CFT. ADS is the theory in the bulk, which is supposed to describe what we want to describe, quantum space-time. Okay. Except that ADS means anti-de Sitter, which is a space which a negative cosmological constant, which does not describe the world in which we actually live, which is de Sitter, not anti-de Sitter, which is a positive cosmological constant. So this is a beautiful example in the realm of mathematics that string theorists agree. And I just listened to a conference a month ago about, oh my God, what do we know about the negative cosmological constant? Can we do it positively? Yes, we can. No, we cannot. It is impossible. Maybe there is a way of doing that. It's extraordinarily distant from anything that can describe our actual world, which is a positive cosmological constant, which has 3 families of quarks, which has, it's in a different realm. It's not the usual physics in which we have a world which we describe. This is fine for 1 year, 5 years, 10 years, 20 years. But after 30 years, it's lost in the mathematics.
So basically, are you saying this is beautiful mathematics, but doesn't describe our world? Is that the basic point?
Yeah.
No,
okay.
But it's not supposed to describe the real world. The question was, we got deviated from that, was, what are the equations? Is there a way of formulating the equations of string theory? I said there is not such a thing as string theory. There are many string theories. The simplest example of string theories we've discovered are ones in which live in this negatively curved anti-de Sitter space. It is often the case that we want to take a complicated physical system in infinite dimensional space, put it in a box. Anti-de Sitter space achieves that by, putting it in a box. In anti-de Sitter space, even though space is spatially infinite, still it's like being in a box. And because that's, in a sense, the simplest possible global bulk gravitational situation. It is true that we don't know how to do the same for flat space or the world we live in, which at least temporarily appears to be de Sitter-like, which is positive cosmological constant. I agree. That's a shortcoming of our understanding. That's why we're still developing this framework. But for years, for us, it was a great achievement, we believe, and which has had enormous implications for all sorts of areas of physics, to be able to formulate this duality and thereby write down the equations or the way of solving non-perturbatively quantum gravity in this particularly simple case. It is not supposed to be a model of the real world. Now, Carlo remarked that before the cosmological constant or the accelerated expansion of the universe occurred, many people, not just string theorists, but just about anyone who thought about it, believed the cosmological constant had to be 0. Why? Because if not 0, it was so incredibly small that nobody could imagine calculating it. Nobody, as far as I know, ever had any expectation that it would be negative. But non-zero was a surprise, which we still haven't been able to deal with. Nobody has any good idea that I know of why the cosmological constant that appears to be present temporarily, perhaps, or forever, is so teeny by 120 orders of magnitude in natural units. So that's a big and very crucial mystery that we must address, and we do not have any solution for that, for sure. Nobody does.
Well, can I just clarify? Is it true? Carlo made the claim that string theory kind of predicted that, or it was at least more happy to be in a world with a negative cosmological constant.
Well,
I saw you shaking your head.
I'm happy to be in a world where I only have to deal with integers and not with complex numbers. You know, sure, mathematically, yes, we understand the world in ADS much better at the present state of understanding. But that's silly. Nobody expected lambda to be negative. Everyone expected it to be zero for some, because it's so damn close to zero. It's close to zero in natural units to 1 part in 10 to the 120. So the standard physics expectation is there must be some reason why it's zero. That was the standard expectation.
Are you also going to say that nobody expected that there was no supersymmetry at CERN at low energy?
No. Okay, so we go on to supersymmetry. So supersymmetry, by the way, you know, one problem with you, the loopy guys, is they don't, not to speak of supersymmetry, they don't even have fermions in their world.
No,
So,
we do have fermions.
yeah.
We do have fermions.
No.
Hey, let me just interrupt for a second.
Wait. I have a book written with a chapter is called fermions in spin forms and fermions in spin networks.
Right. Okay.
Oh,
I just want to clarify that not everyone might know what fermions are. So if I understand it correctly, we have bosons, which are the force-carrying particles, and fermions, which are like the matter particles. Is that correct?
Yeah, the particles that mediate the gauge forces of electromagnetism and of gravity are bosons. Right. But there are also other bosons like the Higgs field and the Higgs meson, which, you know, everything can be regarded as mediating a force. But matter, ordinary matter, is made of electrons and quarks, and fermions are certainly part of the physical world. So, and the existence of fermionic symmetries was a theoretical discovery of, which actually started in string theory, but it's much more general, of enormous import because it extends our notions of symmetry and provides us, you know, a much larger theoretical framework of relativistic quantum mechanics. But within string theory, it was the reasons for believing in low energy supersymmetry were phenomenological again, coming from data, coming from dark matter, coming from the Higgs mass, et cetera, et cetera. There were many good reasons, and there still are, by the way. Supersymmetry, you know, has only been ruled out in some regions. I would personally think there's a 50-50 chance that supersymmetry will still be discovered at what we call low energies. If the SSC hadn't been canceled, it might be by now. So it's an open question. But string theory, of course, only requires or has built into it supersymmetry at the typical, you know, scale of string theory, which is close to the Planck scale.
So basically at a scale where we wouldn't necessarily expect it to appear.
Which would be very unfortunate. So, of course, there was enormous so what drove the supersymmetry hype, which is, by the way, not so much from string theorists, but from standard particle phenomenologists who wanted to construct models that go beyond the standard model that experimentalists could use to look for phenomena that go beyond the standard model. Supersymmetry is very useful because it's a symmetry. It means that except for the mass scale, which breaks the symmetry, everything is predictable. So you could propose to experimentalists, you could tell them what to look for. And otherwise, if you just say, I know nothing, I just, beyond the standard model, I just try to construct arbitrary corrections, there are hundreds and literally thousands of parameters that enter. And that's not, so experimentalists don't like that. If a theorist comes in and say, here's something, look for this, but there are 100 parameters that you have to measure to parameterize your discovery, they don't like that. Supersymmetry people came and said, okay, with 5 parameters, I can tell you what you're going to find, this and this particle. We don't know exactly, there's still 5 parameters, but this is the simplest. And so they loved that. So it's this, typical conspiracy between excited theorists and experimentalists who are hungry to discover new phenomena.
I agree. That's exactly the situation in which we are. So we have frameworks, we have something which is like quantum field theory, but is also a different way of doing quantum field theory. We have something that works in a case which is not our world. It's just,
our world is, we're very close to our world in this holography game, by the way. Our world as tested is four-dimensional, is governed by the standard model, gauge groups, et cetera, et cetera. We are, where there's a workshop beginning in a few weeks at the ATP on flux tubes in QCD. We're getting closer and closer, and hopefully by the end of the century we'll have gotten there, to connect the string theory ideas to the standard model as it is.
You mean 80 years?
Oh, it should, I think probably 80 years. I mean, I have the comforting thought that QCD is so rich and beautiful.
Yeah, but 20 years
it will take 80 years.
One at a time. Okay,
anyway, it will take a lot of time. These are very difficult problems.
I mean, actually, on that issue, isn't it true, Carlo? You're very good at history of science. Isn't it true that Aristarchus predicted that the world was that the Earth doesn't orbit the sun? Sorry, the Earth orbits the sun, not the other way around. That predicted, I think it was Archimedes that realized that predicted stellar parallax, and that was discovered about 2,000 years later. Is there an analogy here?
Yeah, but there were many people who predicted other things which turned out to be wrong. It's not that because somebody predicts something that necessarily 2,000 years later you find it right. I mean, history of science is full of wonderful ideas. Wonderful ideas. People got excited. People worked on it. When I was young, bootstrap.
Problem is now. So I used to, we used to have other my friends like Shelley Glashow would strongly criticize string theory in the early days. Similar kinds of arguments. These are games that people are playing, and it's wrong, and you haven't succeeded in calculating the mass of the electron, et cetera, et cetera. But anyway, this is of little concern to string theorists now, because the standard model is continuously connected to this string theory framework. There is really no distinction. So, forget about it.
I've never seen a string theory with a model inside. I've never seen one. I remember when Gary Horowitz and company were trying to find one vacuum, one supersymmetry breaking. Now people talk about, the landscape. You have to invoke the entropic principle to justify things. I mean,
can we come back to that in a moment? I just want to
completely.
I just want to move. Hang on, David, 1 sec. I just want to move the conversation in a slightly different direction, because we haven't heard anything about loop quantum gravity yet. And so one of the questions is, well, look, maybe there's no viable alternative to string theory. And of course, Carlo, you believe you have got a viable alternative, at least in some context.
Wait. Let me make this clear, because this is often a source of there's a precise sense in which loop quantum gravity is not an alternative to string theory, because I think one should distinguish two problems, right? And the two problems are separated. And it might be within a certain attempt of solving the two that one want to solve them together, but they are really two separate problems. One problem is unification. I mean, can we write a theory, a single theory in which we can find generativity, the standard model, the strong interaction, blah, 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 everything together? That's the problem of unification. And that was one of the main driving motivation of string theory at the beginning. A completely different problem, as a problem, is quantum gravity. Okay, and quantum gravity is, we know there's a gravitational interaction, is there, we know it very well. We know its classical limit fantastically well because of generativity, thanks to Einstein. How do we describe the quantum properties of gravity, of the gravitational interaction itself. Okay. Now there are arguments, and they're not stupid arguments, they're good arguments that say we cannot solve one without the others. But I don't think they're strong arguments. This argument might be wrong.
How do you turn on that?
Oh, wait, David,
David, wait a minute. Let Carlo finish. Let me.
When I was, in fact, let me go back to when I was a student in Bologna, people were saying that there are two big problems here. One is a strong interaction. There are always resonances out of order. You don't understand them. It's very complicated. And there's what is going on there. And the other is that quantum field theory requires renormalization. This is ugly. People hated the renormalization.
Can you just explain what is renormalization, Carlo?
Renormalization is the fact that when you do calculation, you get infinities. You get the result equal infinity, which make no sense. But there is a complicated trick which sounds tricky, or at least sounded tricky a lot, of throwing the infinity under the carpet and computing differences between two infinities that turn out to be finite and comparing with experiments. And this worked very well. It worked for quantum electrodynamics. Richard Feynman and company got Nobel Prizes and fantastic results. But people consider it, and some people still consider it, something which we're missing about the world. And when I was a student, it was the mantra, it was the ideology, it was the dogma that the two problems were going to be solved together. Namely, we're not going to understand the strong interactions unless we have a theory without renormalization. We are not going to understand renormalization. And there were good hints for that, because the strong interaction don't have a good perturbation expansion, so you have to do in some sense some perturbative, blah, 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 blah. Okay? So I grew up with this dogma. And then one day, smart guys came out, and one of them is David Gross, who solved QCD, the strong interaction, and found the Lagrangian and the right theory, which works fantastically. I mean, the last calculations with computers, you can compute the ratio of the mass of the it's just marvelously beautiful QCD, and you still have to deal with infinities and renormalization.
So basically,
solving two problems together was wrong. It was good, it was reasonable, but was wrong. So loop quantum gravity is the idea. Careful, because this is often and so comparing loop quantum gravity and string theory in one sense is very reasonable, but in another sense it's completely unreasonable, because loop quantum gravity is like QCD. Okay, it's like we don't know about the unification of everything. We don't know putting everything together. Einstein, the last 20 years of his life, tried to bring everything together, but he didn't know strong interaction, didn't know weak interaction. He was going in the wrong direction. So forget unification, forget the theory of everything, forget the final theory that brings everything together, this great dream, and just ask what happened when you sort of do a measurement where quantum mechanics and generativity cannot be both are relevant. For instance, in the early universe, for instance, in the center of the life of black hole, or at the end of the evaporation of black hole. So loop quantum gravity is just about that. It's a much less ambitious hope that string theory. It's just a theory, a quantum theory of quantum gravity. Like QCD is a quantum theory of strong interaction. And our claim, which I know David disagrees, I'm perfectly open I know he disagrees. Our claim is that as such, so we don't know anything about chiral fermions. You can couple QCD with a weak interaction. It's not, they stay together well. So you can couple loop quantum gravity with the rest of the standard model, but they're not unified. You can just write on top of another. You can do calculations, but all
right. So to summarize, Carlo, I just want to sort of get to the chase. Basically, loop quantum gravity is just a theory of gravity. We take general relativity and we quantize it. Just
so
like
it's quantum space-time. It's just a quantum theory of space.
Not a theory of everything.
And we claim we have a clean mathematical framework, theory in this case, with open questions and open problems. I don't want to put them under the carpet. That it's clear. It's a Hilbert space, a set of operators, it's transition amplitude finite that we can compute, which allows us to compute, for instance, a black hole evaporates, Hawking evaporation, becomes very small. What happened next? We have a calculation we can do, which tell us, and conceptually, what is how to think about quantum space-time in the small.
Right.
This is provided by loop quantum gravity without any, it's not an alternative of the unification string theory, but is a quantum theory of gravity.
Right. So David, tell us, what are your thoughts on loop quantum gravity then? I've heard you saying not particularly kind things about it.
So, you can. I was very nasty with string theory, so you can say all you want.
David, go ahead.
Starting from a phenomenological point of view. So there are two facts that we know about nature. One is there's matter, like us.
Yeah.
Now, the thing about gravity is gravity couples to everything. Everything experiences gravity. There is no way, I believe strongly, of turning off the other forces of nature or eliminating matter. So in the real world, we have matter, for sure, and we have gravity. We have dynamical space-time. Matter, energy, is one of the sources of the curvature, the dynamics of space-time. And there is no way, since everything couples to gravity, of turning off gravity, of turning off these other forces and other matter, except by throwing them out completely.
Again.
Well, one second, let me finish. I can consider, and we do, the standard model and ignore gravity. Why is that? Why am I allowed to ignore gravity? We all know gravity exists, pulls us in our chair. Why can I ignore it when I calculate the level, the form of atoms and molecules and QCD? I can ignore it because at the scales where we do experiments, gravity is extraordinarily weak.
I agree.
Turn off gravity. It makes sense. We understand that gravity is unimportant at low energies, at large distances. Okay?
Agree.
Understood, accepted, experimental fact. It is believed by many, there are extremely good arguments, that gravity is in a sense, the weakest force in nature. This has to do with the properties of black holes and very deep issues. There is no way of turning off the other forces compared to gravity.
I agree.
It violates that. You cannot turn off the rest of the world in any way we believe of approaching nature. So, and he agrees. So that makes one feel uneasy about trying to do what one often does in physics. Let's just consider quantum gravity by itself. Let me finish.
Wait, Carlo.
It is legitimate. I can, try to do that mathematically, but it bothers me. Second of all, the other traditional approach in physics is we have theories and frameworks which we understand and are well tested experimentally. A great example of one great example is Maxwell's theory of electromagnetism. Enormously successful. The first field theory one had, explaining electricity and magnetism and everything. And when quantum mechanics came along, it was imperative to reconcile Maxwell's classical theory of electromagnetism and quantum mechanics. And that was done by so-called quantizing Maxwell's theory. And the starting point for that, and by the way, for all other early applications of quantum mechanics, was the very firm foundation we had experimentally and phenomenologically with the classical theories of Newton, of Maxwell, and then that guided us in constructing consistent quantum mechanical theories. Always the fact, as Bohr used so forcefully, the correspondence principle. The fact that there are limits one can take for phenomena which are well described classically. Now, in the case of gravity, we have a very successful classical theory of gravity. It's called Einstein's theory of general relativity. We have now observed gravitational waves and can, using these classical equations, calculate the waveforms and test them with observation. So it is a remarkably successful classical theory. It is understood by, among the rest, Einstein, that this is an effective field theory, even classically. There is no reason, and Einstein, was perfectly willing to modify the theory at higher energies or shorter distances.
So hang on. When we say effective theory, I think the public might not understand what is meant by that. Could you just explain?
So typically, what we mean by that is that when we construct theories of physics, it is only a dream that we would have the final unified theory of everything. In a sense, we try to understand physical phenomena at a certain scale that we probe them. And we have tools for doing that and for trying to correct that description if one goes to outside the original domain. For example, to shorter and shorter atomic distances or higher and higher energies, where we begin to lose control. Einstein's theory is...
So it's an approximation, to be short.
The principles of Einstein's theory are sacred in a way, and we believe they will persist. But the explicit mathematical form is, as Einstein himself had always said, going to be corrected. But the standard approach in physics has always been to start with a successful classical thing and reconcile it with quantum mechanics, but always using the classical limit, the cases where the classical theory applies as a firm foundation. One of the most bothersome things about loop quantum gravity is, so far as I understand, and I've taken the opportunity to read a few review articles recently, the lack of, or the enormous difficulty and lack of progress in making that classical correspondence. So one might have a theory of spin networks which has something or other to do with the equations of classical equations of Einstein and the various constraints, but there is impossible so far as I understand, to explain how the moon goes around the Earth, the orbits of the planets. There is no framework in which one can reproduce the classical successes that motivate this whole problem.
All right, so
that is not true. It is not true in string theory. It is, there, and it has been extraordinarily important to have the classical limit of string theory, which is, a generalization along the effective field theory lines of Einstein's equations.
Okay, so let me try and summarize then. Basically, two problems. You don't include matter in loop quantum gravity.
And other forces of nature which are believed to have to be for very important reasons, stronger than gravity.
And you can't reproduce the basic, classical equations of gravity.
And you can't explain why apples fall from trees or the moon goes around the Earth.
Okay,
you
Carlo,
can't.
You want to address that?
Well, and calculate the quantum corrections to that. So the first thing in success of quantum electrodynamics was to explain the 1% deviations from Maxwell's theory due to quantum fluctuations. Quantum effects often are very small. That's why the classical world is such a good
David, let's have Carlo reply.
Okay, so it's 3 points. Let me address all 3 of them. So this technical. So the first one, I think it's there's some language misunderstanding here. Loop quantum gravity does not unify gravity with Young-Mills and fermions. Okay, in the same sense in which QCD is not a unification with the Weinberg-Salam, with the electroweak sector. They're not unified. They sit next to one another. QCD, it's its group, and gluons, and the electroweak interaction, it's its own SU2 plus U1, it's its own theory. Attempt of unifications like SU5, which failed experimentally, SO10, which is still possible, and string theory, which is a much larger, makes gluon, W, electrons, quarks, all manifestation of the same thing, the string, the same entity. So that's a unification. What I'm saying is that loop quantum gravity does not attempt this unification, but I've never said, and it's a misunderstanding to think that loop quantum gravity just works without matter. That's not the case. Loop quantum gravity works with Yang-Mills and fermions.
So can we just explain what is Yang-Mills? That's not something, again, a phrase everyone knows.
Yang-Mills is QCD, for example, the generalization.
The theory of the strong force, basically.
Yeah.
But you don't describe Yang-Mills theory in terms of spin networks.
Sorry?
David, let Carlo finish, please. Let Carlo finish, and then you'll get a chance to respond. Don't worry.
Spin networks with additional, in which the group is SU2 plus SU3, in which there is the internal SU2 and there is the you compute SU3. It's very easy. The reason is not much studied. It's something else, but the questions are there. It's just take my book, and there is a chapter on how to couple Yang-Mills and fermions. Now, if you want to make a technical problem, you might talk about the Higgs, because scalars is a bit tricky. So that's a technical problem. Let's consider this a technical problem. So
just in plain English, Carlo, the claim that you don't have matter is not, you're saying is not correct, that you can
No, it's not correct. There is matter.
Okay, all right, that's good. Plain English answer. Next, the second point.
Now, the second point is a classical limit. Now, the classical limit was a big difficulty of loop quantum gravity in the 90s, 30 years ago. There have been theorems. I mean, the Barrett theorem connect the spin form, the covariant version of the theory to the Einstein equations.
Which, by the way, which covariant, from what I understand by reading, there, people I respect, like Herman Nicolai, the constraint equations have an arbitrary number of solutions. There are no.
If you look at the covariant theory, I mean,
yes, the covariant theory.
Wait. We're getting a bit too technical, guys. People won't know what covariant theory means. So if you could.
So loop quantum gravity comes into formulations.
Yeah.
There are two ways of writing it. It's very much like
the original way of loop quantum gravity, the governing principle of diffeomorphism invariance was broken. So they were willing to break even special relativity. Spin foam is supposed to be an attempt that goes beyond that, but not one that I understand, or how they formulate the, solve the constraint.
You've been studying loop quantum gravity, David. I mean, this is it's great.
Hey, it's a very difficult task.
I know. I've been studying string theory. I mean, I went through the.
Hang on. But before, I just want to get Carlo to finish this point about the classical.
So my claim. I mean, we can
finish that point.
We can go into the.
So let me ask you. I mean, is it possible for you to calculate the gravitational corrections?
Yeah. This is the third point. Let me go precisely. Let me address
the moon's orbit.
Yeah. So I want to claim that one has some theorems that connect the theory to the Einstein equation. Now, of course, I mean, you know well how is mathematical physics. I mean, do you ever really a proof that string theory is finite? No. But do we believe it? Yes. Does Carlo believe it? Yes. But is there a proof? No. So there are. You can always.
I'm not arguing about rigor.
Exactly. So then we're on the same level.
I was asked the question what I think about loop quantum gravity, and there are obviously very interesting spin network results there. But what bothered me was these, sort of very primitive reactions, which are no matter, no gauge,
no matter. I think
no Higgs, no classical limit.
there is a classical limit.
There might be.
Hang on, let me interrupt.
Let me go to the third point, because the third point is an interesting one. I think.
Hang on, Carlo, wait, Dave, guys, wait a second. We only have about 15 minutes left. So I just want to see if I can summarize this, right? So basically, if I understand correctly, what David is saying is you can't prove that you can reproduce classical gravity. You're saying, well, it's not, we can't prove it, but we have arguments in the same way that you can't prove that string theory is finite, but there are very good arguments, and they are convincing arguments. Is that a good summary of where we're at on this point?
Yeah, I don't think it's comparable. It might be possible, of course, but the feeling among people who've dealt with problems of renormalization, non-renormalizability, quantizing theories like Einstein's theory, is that eventually, when they try to push this to the state where they could make calculations of the gravitation, the gravitational corrections to observables, or reproduce the motion of the Earth around the sun, they're going to run into exactly the same problems.
Well, that's a feeling of people, not the people who
just telling you what my prediction would be.
Okay.
And from what I understand from the literature and the incredible fights within this community, my God, Bourgeois versus Ashtekar, they each testing, complaining about the other people's implicit assumptions, so that they're going to run into trying to make this precise.
Sorry, can I just explain what that is about?
Same problems that one follows by standard procedure of trying to quantize Einstein's theory.
Okay, so let me just give a context there, because people might not know what I was referring to there. That Abai Ashtekar has worked a lot on what's called loop quantum cosmology, attempts to build a theory of the Big Bang, and it predicts a bounce so that there is a contraction and expansion. And Martin Boerewald, who was one of the people that worked on that, has said, no, it doesn't work. He thinks it's more like, I think, a Hartle-Hawking state. So Carlo, if you can just respond to that, and then we've only got 15 minutes left. So I want to move us off to one or two other topics. And so
I want to, Phil, I want to answer to the third point.
Yeah, of course.
Of David before, because I think it's beautiful and it's subtle. There's one problem here. The problem is that the first order in HR, the one loop corrections to say generativistic predictions at relatively low energy. The problem is that we know them. That's why we already know them, because if you take just non-renormalizable GR and you treat it as an effective field theory and your calculation of one loop, like Dono does or others, you can compute the first order correction to the Newton potential. And I believe that this is pretty reliable. And I believe that the day in which in string theory in 4-dimension, blah, 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 you could do the full calculation, and the day in which loop quantum gravity, you could do the full calculation, you will find that.
Oh, no, it's profound. It's trivial. That's not a problem. The problem, of course, is in effective field theory.
Finish one.
You have an infinite. If you go beyond one
loop, you never finish an argument. You immediately jump. Please.
All right, let Carlo finish, and then you'll respond, and then we're going to move on to a different topic. We don't have a lot of time left.
I think, and that's the beauty of the story, that in quantum mechanics you have two typical effects. One is the thing like small corrections to classical prediction, and the other is strong quantum effects like tunneling, things that don't happen classically, things that go to the exponential e to the -1 of h bar, things like that. That's where we're going to see quantum gravity, I think. And for instance, what happened at the end of a black hole evaporation should be something like tunneling, not a small corrections to classical evolution. If you're going to really do the physics of the Big Bang, which, let's be honest, there are great attempts in strings, in loops, perhaps others, but we're confused about that, right? We don't have a clear picture of what happened. That's going to be a non-perturbative effect. So,
what do we mean by non-perturbative, Carlo? Sorry, can you explain that?
In quantum mechanics, predict some small correction to classical, but then predict some strong things that would not happen classically at all. And radioactivity, it's an example. I mean, inside a nucleus, there's something which is trapped, but quantum mechanics can tunnel it out, and that's radioactivity. And this you cannot compute this first order perturbation theory. You have sort of to go the other way around, to go to the strong non-perturbative regime. And I think this is where the interesting calculations are, and where in loop quantum gravity we are focusing. For instance, in the end of the black hole evaporation, or trying to do. So my answer is that you can do matter. You have arguments for strong arguments for the classical limit. The first order calculations we already know, and you can derive that, but that's zero. And the real interesting quantum phenomena is what happened to a black hole at the end of the evaporation. That's the kind of realism. The day in which I'll see a convincing calculation of that, I will be theoretically happy about the quantum.
It's rather difficult to formulate what the hell that means in terms of physical observables.
That's exactly what quantum is strong.
One at a time. Carlo,
David, that's exactly where quantum gravity is strong.
Yeah,
So
in loop quantum gravity, I never understand what observables are. You write down some formula for the area of something. Look, but
David, what do we mean by what are the observables? I think the public won't understand what that statement means.
So in other words, what you actually do, what an experimenter actually does. When one tries to discuss physics, we try to discuss what you can actually measure and make predictions. But again, one area we haven't discussed is the success of both attempts to deal with the theoretical imperative is to understand black holes and what happens for black holes. And there, I will defend string theory's great success in one, showing that in many cases where one has control in particular string theories of black holes, that one can calculate precisely the entropy, the number of microstates of a black hole, and get precise correspondence, including quantum corrections, to Bekenstein's-Hawking's famous formula. And more recently, with the aid of holography, understanding the so-called page curve, the thermodynamic description of the entropy, the number of the information contained in a black hole as it evaporates. So these are major milestones which, by the way, convinced Hawking towards the end of his life that information gets out of a black hole, that we don't lose the information in the collapse and radiation of a black hole. So I think these are major theoretical successes. And one of the things that, by the way, convinces people who are not die-hard string theorists that string theory is on the right track. This is a non-trivial thing. This has been attempted in loop quantum gravity. They admit they have a parameter that they can fix. You know, they can't make a precise prediction. But it's much more than that. Black holes are much more than just the formula for the number of microstates. It's also the evolution, the evaporation, and eventually the kind of question that Carlo is asking, which we're still not sure of. Some people believe there is no inside of a black hole, fuzzball. Some people believe there is. Still the resolution of what the singularity of the Schwarzschild solution means, the Lorentzian, is unclear. There is a lot yet to be understood, but the progress of, especially with holographic techniques of understanding black hole quantum mechanically, is incredibly impressive.
Okay, so let me just summarize. Basically, string theory is an amazing success at computing the entropy of a black hole. Loop quantum gravity can do it, but only if you fix this particular parameter, this free parameter called the Immerzi parameter. And so therefore, it's not as convincing as what happens in string theory. Carlo, do you want to respond to that?
This was a situation a number of years ago. It has changed because the calculation of the black hole entropy is done in a much more convincing way. without a free parameter. But I think the interesting part is the second part, which is the page curve. And here again, this
can you explain what is the page curve again? I think the public...
Yeah. I'm gonna explain exactly what the situation. This has to do with the famous problem of what happened to the information that falls inside a black hole. I mean, we see things falling in, and in a metaphorical way, you can think you can throw an encyclopedia in. There's a lot of information, a lot of details. And if the black hole evaporates, like Stephen Hawking are convincingly argued, it has convinced all of us that this is the case. And if at the end of the evaporation, the black hole disappears into nothing, all this information seems to be lost forever. Because there is stuff that comes out from a black hole, which is the heat of the black hole that Hawking has calculated. But this heat, it seemed at the beginning of Hawking calculation that has no information at all. It's thermal, it's just mixed. It's just random, so it's lost information. So nowadays, the community has split in two parts in a very funny way. Each one is convinced that the other is completely not understanding anything, okay? And it's really, in spite of a lot of listening to one another, there is really a split. And each part is convinced that it has a solution, and the other is wrong, okay? And one part, which is the one David was referring to, got convinced that inside the black hole, there are no states. There's no information really inside the black hole. Okay, then the possible number in which the black hole can be, it's only given by this famous formula that David was referring to, the entropy of black hole, which is the number of states of black hole. And when the black hole shrinks because of evaporation, okay, it has less states. And the heat that come out recover the information that was sent before. So there are some funny correlations between the heat coming out at some time, the heat coming out at some other time. So the actual information stored in the black hole does not grow; it comes down, and this is a page curve. It goes up and comes down. Okay, this is what half of the community got convinced from. And this is based on what the same half of the community sometimes call the central dogma. And I think the name dogma is particularly useful here. They call it dogma, which is a belief that indeed this thermodynamical entropy, so this number of states of the black hole, includes also the thing that you can distinguish if you go inside the black hole. So inside the black hole, there is no more information than this entropy, which is given by the area, which shrinks. The other half of the community, okay, to which I mostly talk, but then I talk also with Don Marrows of Steve Giddins or what's the name? Oh, sorry, I'm bad with name. The other half of the community believes that that picture is nonsense. It's a dogma is a dogma. Like, well, I'm not going to mention dogma because I'm going to offending somebody. Namely, that the number of states counted by black hole entropy, the area, only refers to states distinguished from the outside, but there are states inside. Inside is a long tube. The black hole is a huge space inside. So when the black hole shrinks, there's no page curve that goes down. There is no, the thermal radiation is really thermal radiation. The black hole becomes very small, but the information is still inside. Okay? And then we are really in quantum gravity. Then we need quantum gravity in string theory, in loop quantum gravity to say what happened. And we cannot avoid that, because one possibility is that quantum gravity tells you that there is a little remnant after the end of the evaporation from which the information is going to come out in a long time, in a very long time. So there are two expectations. It's beautiful. It's just a big debate at the foundation of science. Concrete situation, okay, black holes are real, we know, there's zillions out there in the sky. Presumably they're all going to evaporate, we're all convinced. At some point, seems they all going to evaporate, become small, and then what? And this may even have a astrophysical consequence, because if there were primordial black holes, which is possible, we don't know, but it's possible, some small primordial black hole might have already evaporated. So these remnants might be there. And now we are in the realm of attempt speculations, but also in the realm where possible measurements could come out to distinguish and to tell us one picture is right, one picture is wrong. So once again, I think all this conversation, what I wanted to point out is that there's nothing wrong in discussions going on in fundamental physics when we don't know, when the problems are open. But the problems are open. And the page curve, the dogma, ADF, CFT, supersymmetry, string theory are a cluster of ideas which might be right or might be wrong. And there are a lot of people who are following not just loop quantum gravity. I don't want to say that the only alternative is loop quantum gravity.
We should mention there's causal set theory, causal dynamical triangulations.
People following different things. I don't want to make a list of the good and the bad, in my opinion. But definitely there's a large community which is not convinced. In fact, it's much less convinced than it was 20 years ago that this big sort of mathematical adventure, which David says still young, is still young, but it's 50 years. So it hasn't delivered yet.
Okay, I want to just drive. We're running out of time, I'm afraid. So I want to come to one last point, and then we can sum up. And this is a criticism that's been put forward against string theory, but might be applicable to loop quantum gravity as well. And that is that for anything to be science, it has to make falsifiable predictions. String theory doesn't make falsifiable predictions, therefore it's not science. Now, now that might be true of loop quantum gravity as well. So, David, if you could start off, is this actually the right way to demarcate between science and non-science? Well, and what do you say about making predictions from string theory?
So as somebody who has made, in some sense, literally thousands, if not millions of predictions, which have been tested now over and over again, QCD is a marvelous factory for predictions. Since at high energies, you can calculate with arbitrary precision, and experimenters measure billions of events every second at LHC. Absolutely, that's the goal of physics and the ultimate test. I feel sorry for the people doing loop quantum gravity because there I see no hope. I can't imagine, unfortunately, ways of testing quantum effects in quantum gravity. It's really difficult. String theory still has a possibility of the framework of making contact with the unified beyond the standard models that we were hoping for back then. Although that might take another century, who knows? But the science does what it has to do. We're curious. We want to understand the real world. There's nothing like experiment to guide us. I mean, I've lived through periods where experimenters pointed the way and helped us find the standard model. And without that, we'd still be futzing around with who knows what. But we're stuck now in a period of disparate scales. Everyone knows that there's fantastically different physics at the Planck scale. Planck scale is 20 orders of magnitude away from observation. And there, so far, doesn't appear to be anything that gives clues along the way. So what do? Well, we can't just throw up our hands and go home because we're curious. So we have no choice, really, but to try to pursue along a theoretical line. And it is very dangerous, very dangerous. You could easily go off in wrong directions. One of the great advantages of string theory, again, is one, it has a nice classical limit, which connects to our classical theories of, say, general relativity, which is so mysterious in the quantum regime. Two, because of the understanding now of the holography, it is connected directly, mathematically, to theories we understand much better and which can be tested experimentally. And remarkably, it's not just the gauge theories that describe the standard model, electricity, the strong, weak nuclear force, but also other quantum field theories which are useful in condensed matter physics and nuclear physics. So we have many places where we can connect these ideas that we're developing mathematically, theoretically, to real physics, and thereby draw inspiration and guidance from experiments in those fields.
Okay, Carlo, do you want to address this issue?
Yes. So the issue is, do we need to do experiments, and are we in danger of being without? Well, I basically agree with David 100%, and I can answer by saying that my own trajectory in working in loop quantum gravity has been since the 80s for maybe 20 or more years, the building of the theory. First in the canonical version of it, and then in the covariant version, the two versions of it. And I've then mostly shift to the second because it seems better to me, but it was a theory building. But then I changed because I realized two things. First of all, that there was a theory there. I mean, there's a way of doing calculations. In principle, we know calculations. Theory is there, and it's useless unless we go to nature. And so it is more than 10 years that my work, it's completely focused on trying to apply the theory. In fact, I spend the time with my students to tell them, stop playing with theory building. Stop, trying to prove that, trying to do rigorous, try to make a little model a little bit better because you think that's not the interesting thing. The interesting thing is go back to the nature. And if you have a chance to measure quantum gravities in the sky, and in fact, Bayashneker, who was one of the architect of the story, has totally shifted from the developing of loop quantum gravity to apply loop quantum gravity to the Big Bang in the hope of seeing traces in the cosmic background radiation. He used the canonical theory.
Just to clarify, he's saying that we have a collapsing universe and bounce and expand.
And then, but then the point is that can from that compute something that I see in the CMB, and maybe some anomalies with respect to the standard model, the cosmological standard model, not yet there, but that's a good project to try to find there. And I've been working in black holes, and I have papers on are fast radio burst, can fast radio burst be interpreted? Some of them so and so question mark. And nowadays I'm working on dark matter. Can dark matter be interpreted as remnant of primordial black holes? If so, we would already have evidence of quantum gravity, because remnants, what happened at the end of the evaporation is that, something remarkable happened with black holes, classical black holes, no quantum gravity here. People searched for classical black holes, right? And people were not convinced that they didn't exist. But in fact, Sagittarius A star, the super big black holes at the center of the galaxies, had been detected since the early days of radio astronomy without realizing that was a black hole. For a few decades, people were getting the signal from that funny thing very strong. I mean, if we had ice in that range in the radio, we would see a shining thing like there, and the antenna just saw it. And it took forever to understand what it is. So it could even be that something like dark matter, which we don't know what it is, it's a phenomenon that we're going to understand with quantum gravity. Might be. I might be wrong. This is one of the hypotheses I am following. But this is to say, to answer in the same direction as David, namely, it's only the moment you can do theory without experiments. Einstein did, Copernicus did. I mean, it's no doubt. But it's only when then your theory becomes predictive, of course, that you say, okay, now I really believe it.
Okay, so maybe we can end, there may be some common ground here then, because it's been alleged that people that work in quantum gravity work in this esoteric mathematical world that's got nothing to do with experiment. And in fact, some people have alleged that the people working in this field don't even care about experiments. But it would seem that we've got some common ground at the end here, that we do think ultimately theory may help us decide what's plausible, what's a good candidate to work on, but ultimately it is experiment that will decide what is really true. Would both agree on that?
Well, it's the real world that has decided what is true. An experiment is a way of testing our ideas. I mean, it's always easy to come up with all sorts of speculations, but we're often wrong. So, that way of testing our ideas has proven to be very sick. That is the heart of the scientific method, and proven to be a hell of a good strategy, which unfortunately only part of the population subscribes to.
Right.
But the greatest invention, in my opinion, of humankind. So we really need that. And you look for those clues from the real world wherever you can find them. And as I said, what keeps string theory, for this, whatever you want to call it, is labeled string theory, going, is, I believe, at least keeps me going, is the connections to the real world, either in a variety of ways to effective theory at low energies, or through the holography to theories we understand and continue to explore their structure. So, for example, again, to end our conversation where it began, string theory began with an attempt to understand flux tubes of QCD. That still is an ongoing goal, which is being informed now. We just have, as I said, a workshop beginning at the KITP on this, informed by experiments, new discoveries at the LHC on multi-quark states, by lattice calculations in QCD, and by ideas coming from string theory, which hopefully by the end of the century will enable us to have analytic control of nuclear states, nuclear forces.
Okay. So, Carlo, final words, and then I think we should
just, let me just close by saying that David and I often have been, how to say, rough conversation between us because of what he is and because of what I am. But I think it's obvious. I have a lot of sympathy for David, and I do it with pleasure. Not last, as I said at the beginning, because I think he's like Einstein a little bit. He did fantastic physics in his youth, and then got lost in the second part of his life in a useless theory.
All right,
let me end by complimenting Carlo, whose recent papers on time and quantum mechanics I've enjoyed a lot, and it would be nice to have a friendly conversation on such issues. But I think he does the best when he retreats to philosophy.
Well, look, thank you guys. It's been a really fun conversation, and we only covered a bare fraction of what I was hoping we'd cover, but of course that's inevitable. I really want to thank you both, and for those watching, if you've liked this, please hit the like button, leave your comments, and if you have any other suggestions for other topics that you'd like to have, we're all ears. So thanks again. Thank you, everyone. Bye-bye.
Thank you, Phil. Thank you, David. Bye-bye.
Bye.
Bye-bye.